welcome. Today we're going to be tackling some really core calculations in radiation physics.
That's right. Stuff that's super important for anyone working with radioactive sources.
Yeah, absolutely critical, not just for, boards, but for everyday clinical work too.
Definitely. They guide decisions all the time.
So we'll break down the key math behind radioactive decay itself.
And then we'll get into effective half-life, which is really crucial.
And also how to calculate the total dose from those permanent brachytherapy implants, the seeds.
Exactly. And the goal isn't just like memorizing equations. We want you to really get the concepts.
Right. Build that intuition so you can actually apply it confidently.
Whether you're just starting out or deep into board review.
Because mastering this stuff, it really impacts patient care, patient safety.
No question. So where should we start? Decay seems like the place.
Let's do it. Radioactive decay, the absolute starting point.
Okay, so radioactive decay. It's basically when an unstable atom, the nucleus, decides it wants to be more stable.
And in that process, it releases energy, right? Radiation.
Exactly. Particles or electromagnetic radiation. Now, the tricky part is you can't predict exactly when one specific atom will decay. It's random.
But if you have a whole bunch of them.
Ah, yes. If you have millions or billions of these unstable atoms, the overall rate of decay for the whole group becomes very, very predictable.
And that predictability, it's governed by a pretty simple idea, isn't it?
It is. The rate that atoms decay is just directly proportional to how many radioactive atoms you had at that moment.
Makes sense. More atoms, more chances for one to decay in any given second.
Precisely. If you have 1 million atoms, you expect more decays per second than if you only had, say, 10.
So how do we quantify that relationship?
That's where the decay constant comes in. We use the Greek letter lambda. It's kind of like a cursive L.
I know.
And lambda tells you the fraction of the atoms you have that will decay per unit of time. So per second or per hour, whatever your unit is.
Oh, bigger lambda means faster decay.
You got it. A large lambda means a big chunk of your atoms decay quickly, high decay rate. Small lambda, slow decay.
Okay, lambda is fundamental. But honestly, it's not always the most intuitive concept, right, when you first learn it.
That's fair. I think the idea that clicks more easily for most people is the half-life.
Ah, yes. T sub 1/2, capital T subscript 1/2.
Exactly. And the half-life is just, well, it's the time it takes for exactly half of your radioactive atoms in a sample to decay. Simple as that.
Doesn't matter how much you start with.
Nope. A gram, a microgram. After one half-life period, half of the radioactive stuff is gone. It's decayed into something else.
That halving idea is key.
It really is. Start with 100 atoms, wait one half-life, you've got 50 left.
Wait another half-life.
Down to 25, then 12.5, and so on. It just keeps halving the remaining amount. It's an exponential decrease.
And lambda and half-life, they're connected, right? Inversely.
Beautifully connected. If you know one, you can always find the other. It's a simple mathematical relationship.
Okay, what's the formula?
Lambda equals the natural logarithm of 2 divided by the half-life, t sub 1/2.
Natural logarithm of 2 ln 2.
Right, and ln 2 is approximately 0.693. It's a number you see a lot in this field.
So the practical formula is lambda equals 0.693 divided by t sub 1/2.
That's the one you'll use most often. 0.693 euros. Makes converting back and forth really easy.
And it shows the inverse relationship clearly. Short half-life means big lambda, fast decay.
Exactly. Long half-life, small lambda, slow decay. Makes perfect sense.
Okay, concepts down. Now, the actual calculations. How do we figure out how much activity or how many atoms are left after a certain amount of time?
Right. This is where the rubber meets the road. We need the decay equation.
The formulas, yeah?
Yep. There are two main ones people use. They look different, but they describe the same process.
Okay, give us the first one.
The first one uses lambda, the decay constant. It says the activity at any time, let's call that AT, equals the initial activity you started with, A0, multiplied by E.
E, the base of the natural log, like 2.718.
Right. Multiplied by E raised to the power of negative lambda times T. So AT equals AEE.
A of T equals A0 times E to the power of minus lambda T. That minus sign is important, right?
Crucial. It shows the activity is decreasing, decaying away over time.
Makes sense. What's the second form? The one using half-life.
This one often feels a bit more intuitive for folks. It says the activity at time t, AT, equals the initial activity, A0, multiplied by 0.5.
Half.
Exactly. 1/2 0.5 raised to the power of the elapsed time t divided by the half-life, t sub 1/2. So AT equals A.5.
Okay, A of T equals A, 0 times 0.5, raised to the power of T over T 1/2.
Yeah. And that exponent, t divided by t 1/2, it's literally just telling you how many half-lives have gone by during the time t.
Ah, okay. So if t equals 1 half-life, the exponent is 1. You get a0 times 0.5 to the power of 1, which is half of a0.
Perfect. And if t equals 2 half-lives, the exponent is 2. You get a0 times 0.5 squared.
0.5 squared is 0.25 a quarter.
Right. So you have a quarter of your initial activity left after 2 half-lives. It matches that halving concept exactly.
So these two equations, the E1 and the 0.5 one, they're mathematically the same thing.
Totally equivalent. You can derive one from the other using that lambda equals 0.693 over t 1/2 relationship. Which one you use just depends on what info you're given, or maybe just which one you prefer.
A 0 is always the starting activity. AT is what's left after time t. And activity, that's measured in, like, curies or becquerels.
Yep, curies, Kenny, becquerels, BQ, or often millicuries, MCI, or megabecquerels, MBQ. Those are the common units.
Okay, so if I'm faced with a decay problem on an exam or in the clinic, what's the game plan? How do I attack it without getting tangled up?
Good question. A systematic approach is best. Step 1. Lay out what you know and what you need to find.
Okay, list the variables. Initial activity, final activity, time, lambda, half-life.
Exactly. Get clear on your knowns and your target unknown.
Then what?
Step 2. This is huge EE. Check your units, especially time units.
Ah, the unit trap.
It gets people all the time. If your half-life is in days, but the time elapsed is given in hours, you have to convert them so they match before you plug anything into the formula.
So everything in days or everything in hours. Consistency.
Paramount. Cannot stress that enough. Mixing hours and days or minutes and seconds, it's a guaranteed wrong answer.
Okay, units matched. Step 3.
Make sure you have the right decay parameter for the formula you chose. If you're using the AUO formula, you need lambda. If you're using the A0.5 formula, you need the half-life.
And if you have one but need the other?
Use the conversion. Lambda equals 0.693 divided by t 1/2, or rearrange it to 2 1/2 equals 0.693 divided by lambda.
Got it. Convert if needed.
Right. And finally, step 4, you've got your variables listed, units are consistent, you have the right decay parameter. Now you plug the numbers into the chosen decay formula and solve for whatever you're looking for.
Okay, that makes sense. Identify, check units, get lambda or half-life, plug and chug.
Pretty much. Now, sometimes the problem is flipped.
How so?
Sometimes you know the starting activity, A0, and the activity left now, AT, and you need to figure out how much time T has passed.
Ah, solving for time. That sounds like...
Logarithms.
Ding, ding, ding. You need logs, specifically the natural logarithm, ln.
Okay, walk me through that. If we use AT equals AE.
First, isolate the exponential part. Divide both sides by a0. So you get AT divided by a0 equals e to the minus lambda t.
Okay, ATAAE. How do we get t out of that exponent?
Take the natural log, ae, of both sides.
Yeah.
The natural log is the inverse function of e to the power of something. So ln at e to the minus lambda t is just minus lambda t.
Okay, so LNATA.
Exactly. Now just solve for t. Divide by minus lambda, so t ln lnat.
Or sometimes it looks cleaner if you flip the fraction inside the log, right? Using log rule.
Yep. LNATA is the same as LNAAT, so you can also write it as T ln AAAT. The negative signs cancel. Might be easier to avoid losing a negative sign that way. So calculate the ratio of initial to final activity. Hit the LMN button on the calculator for that ratio, and then divide the result by lambda.
That's the process. You can do a similar thing starting with the AT of ON, 0.5 form. Take the natural log of both sides.
Right. LNAT ln, 0.5. Then use log properties.
Yeah, the exponent comes down, so ln, AT, AAA, and ln 0.5.
And ln 0.5 is a known number. It's actually minus ln2, or about minus 0.693.
Exactly. So you can rearrange and solve for t. Or sometimes if the ratio ATA is a nice power of 0.5, like a quarter or an eighth, you can just figure out how many half-lives it represents.
Like if AT is exactly 1/4 of A0, TT must equal 2, because 5 squared is 0.25.
Precisely. Then you just solve t equals 2t. That's often quicker if the numbers work out nicely. If not, logs are the way.
Let's try that glow stick analogy you mentioned to really cement the halving idea.
Okay, imagine you crack 100 glow sticks at once. That's your A0. Let's say these are special 30-minute half-life glow sticks.
So after 30 minutes,
Only 50 are still glowing brightly. The other 50 have faded out.
after another 30 minutes, so 60 minutes total,
Those 50 are halved again. You're down to 25 glowing sticks.
90 minutes total.
Half of 25. Maybe 12 are glowing, 1 is flickering, you get the idea. If you walked in later and counted only 25 glowing sticks, and you knew the half-life was 30 minutes?
I can work backward. 25 is 14 of 100. That's 2 halvings. 2 half-lives must have passed. So 2 times 30 minutes, 60 minutes ago.
Exactly. That repeated halving over fixed time intervals is the essence of decay and half-life.
Yep.
It applies to HDR sources, I-131 in patients, nuclear medicine drugs, everything.
Okay, solid foundation on decay. Let's level up. Concept number 2, effective half-life.
Right. This is where reality gets a bit more complex, especially in biological systems.
Because it's not just about the atom decaying.
Correct. Often, particularly in nuclear medicine, you inject a radioactive substance. It decays physically, yes, based on its isotope properties, but your body is also trying to get rid of it.
Biological processes, like peeing it out or metabolism.
Excretion, metabolism, sweating, breathing it out, all sorts of biological clearance mechanisms are also working to remove the substance from your body or from a specific organ.
So you have 2 things removing the radioactivity simultaneously.
Exactly. And when both are happening, the substance disappears from the body faster than either process would achieve on its own.
Okay, so let's define the terms clearly. We have the physical half-life, T physical.
Yep. That's just the standard radioactive half-life of the isotope itself.
Yeah.
How long for half to decay if it were just sitting in a vial?
And then the biological half-life, T biological. Need to say that one clearly. Biological.
Right, too biological. This is the time it would take for biological processes alone to remove half the substance from the body, assuming, just for the concept, that it wasn't radioactive at all.
Okay, physical decay, biological removal, put them together.
And you get the effective half-life. T effective. This is the actual time it takes for the amount of radioactive stuff in the body or organ to decrease by half, considering both processes working together.
How do we visualize that?
Yeah. Think of a bucket being filled with water, maybe. That's the dose administration. Now imagine it has 2 drains.
Okay.
One drain is physical decay. It lets water out at a certain rate. The other drain is biological clearance. It lets water out too, maybe at a different rate.
If only one drain was open, the water level would drop at that drain's rate.
Right. But with both drains open, the water level drops much faster, doesn't it?
Yeah, because water's leaving through both holes.
That combined faster drainage rate is analogous to the effective removal. The rates of removal add up.
Ah, so it's not the half-lives themselves that add.
No, that's a common misconception. You don't add T physical and T biological, you add their rates. And the rate of removal is like inversely proportional to the half-life. Think of it as 1 over T.
So the effective removal rate, 1T effective, is the sum of the physical removal rate, 1T physical, and the biological removal rate, 1T biological.
You've nailed it. That gives us the fundamental formula. 1 divided by T effective equals 1 divided by T physical plus 1 divided by T biological.
1 over T effective plus 1 over T physical plus 1 over T biological. Okay, that's the core equation. How do we use it to solve problems?
Same strategy as before, really. Step 1, identify what you know and what you need. Usually you'll have T physical and T biological, and you want T effective.
But maybe sometimes they give T effective and T physical and ask for T biological.
Could happen. The algebra works the same way.
Step 2, I bet it's units again.
You know it. Check the units of T physical and T biological. Are they both in hours? Both in days. They must be the same before you use the formula. Convert if needed.
Okay, units matched. Step 3.
Plug the known values into the formula. 1T effective equals 1T physical plus 1T biological. Calculate the right-hand side, add those fractions, you'll get a number.
So now I have a value for 1 over T effective. Let's say it's, 0.25 per hour.
Right. And now comes step 4. The step everyone forgets at least once.
Don't forget the flip.
Exactly. The number you calculated, 0.25 in your example, is 1 over T effective. To get T effective itself, you have to take the reciprocal, flip the fraction, or calculate 1 divided by that number.
So if 1 T effective equals 0.25 per hour, then T effective equals 1.25 hours, which is 4 hours.
Perfect. Forgetting that final flip is probably the single most common mistake on these types of exam questions.
Is there a way to double-check yourself? A sanity check?
Yes. The mnemonic. The effective half-life, T effective, must always be shorter than both T physical and T biological.
Why?
Because both processes are removing the substance. The combined effect has to be faster removal, which means a shorter time to get rid of half of it.
So in my example, T effective was 4 hours. If T physical was, say, 6 hours and T biological was 12 hours, 4 is shorter than both 6 and 12, so it makes sense.
Exactly. If you calculate a T effective that's longer than either T physical or T biological, you absolutely made a mistake somewhere. Probably forgot the reciprocal.
That mnemonic is gold. So this whole effective half-life concept, it's mainly for nuclear medicine dosimetry.
Primarily, yes. It's essential for calculating how long a radiopharmaceutical stays in a particular organ or the whole body. That residence time is directly used to estimate the radiation dose delivered. You need to account for both how fast the isotope decays and how fast the body clears the drug it's attached to.
Can you give an example?
Sure, technetium 99 meters, very common imaging isotope. Physical half-life is about 6 hours. If you attach it to a molecule, the kidneys clear out really fast, maybe with a biological half-life of just 1 hour.
Okay, T physical 6, T biological equals 1.
Then 1 T effective equals 16 plus 11. That's 16 plus 66 equals 76 per hour.
Flip it. T effective equals 67 hours. Less than 1 hour.
Right. So even though the technetium itself sticks around for a while, 6-hour half-life, because the drug carrying it is cleared so quickly, the effective half-life in the body is really short. That limits radiation dose to tissues.
Conversely, if it was attached to something the body holds onto for a very long time, like particles trapped in the lungs,
then T biological is very large, so 1 T biological is very small, almost 0. In that case, 1 T effective, 1 T physical. The effective half-life is basically just the physical half-life. The decay itself becomes the dominant factor.
makes sense. Okay, decay done, effective half-life done. Third big topic, total dose from permanent implants.
Right. Brachytherapy seeds like iodine 125 or palladium 103 used in prostate cancer treatment, for example.
These are the tiny radioactive sources we put directly into the tumor or tissue and just leave them there.
Exactly. They stay in permanently. Unlike HDR brachytherapy, where we remove the source after a few minutes, these seeds deliver their dose continuously as they decay away over weeks or months until their activity is negligible.
So we need to figure out the total amount of dose that seed will deliver over its entire lifespan in the patient.
Precisely. From the moment it's implanted until it's essentially fully decayed.
What concepts do we need for that calculation?
2 key things. First, we don't actually use the half-life directly here. We use something related called the mean life.
Mean life, not half-life. Okay.
Yeah.
What is it?
Mean life is represented by the Greek letter tau. Looks like a lowercase t with a little hook or tail. It represents the average lifespan of a radioactive atom in that sample before it decays.
Average lifespan. How's that different from half-life?
Half-life is the time for half the atoms to decay. Mean life considers all the atoms. Some decay early, some decay late. It's the average time any single atom exists before it decays. Mathematically, it turns out that the mean life, tau, is simply the reciprocal of the decay constant, lambda. A hell.
Okay, tau equals 1 over lambda. But we usually know the half-life, not lambda. How do they relate?
Well, since L1, and we know ln2 tas, we can substitute that in. It's 1 ln2.
Flipping the fraction, ln2 ln.
Exactly. And since ln2 is about 0.693, dividing by 0.693 is the same as multiplying by 0.693, which is roughly 1.44.
Ah, so the mean life, tau, is approximately 1.44 times the half-life, t1/2.
That's the really useful approximation. Let 1.44 tau just multiply the half-life by 1.44 to get the mean life.
Okay, so the average atom sticks around about 44% longer than the time it takes for half the atoms to decay. Got it. What's the second concept we need?
The initial dose rate. Call it D0, D0.
Initial dose rate.
When you first implant that seed, it has its highest activity, right? It hasn't decayed much yet. So it's delivering radiation dose to the surrounding tissue at its maximum rate right at the beginning.
That maximum rate right at time 0 is the initial dose rate, D0.
Correct. And it's usually measured in units of dose per unit time, like centigrade per hour, CG-er, or maybe gray per hour, if we sure.
Okay, so we need the initial dose rate, D0, and the mean life. How do they give us the total dose delivered over the seed's entire lifetime?
Conceptually, the total dose is like summing up the dose delivered in every little time interval as the source decays away. It turns out mathematically this integral is equivalent to just multiplying the initial dose rate by the mean life.
Really? That's simple.
The formula itself is simple. Total dose of multiplying initial dose rate, D0, multiplied by mean life.
Total dose, DRO key. That seems almost too easy. There must be a catch.
Oh, there's a catch, and it's our old friend.
Units.
Units, absolutely. This is, again, the #1 pitfall in this calculation, getting the units wrong.
Okay, let's walk through the steps carefully, highlighting the unit issue.
Step 1, identify your inputs. You need the initial dose rate, DRO. That'll be given probably in something like centigrade per hour. And you need the isotope's half-life, 2O, probably given in days or maybe hours.
Okay, got DNT. Step 2,
Calculate the mean life from the half-life. Use that approximation. Error 1.44 DOs.
Calculate tau. Got it. Now, step 3, the units.
This is critical. Before you multiply D and tau together, their time units must be compatible.
Meaning?
If your D is in dose per hour, then your POEM must be expressed in hours for the multiplication to work correctly.
But TOO was calculated from the half-life, which might have been in days.
Exactly. So if TOs was in days, you calculated in days. You cannot multiply D inside a hour by in days. You have to convert one of them first.
So either convert from days to hours, multiply by 24 hours day?
Yes. Or, alternatively, you could convert D from cutty hour to SID day, multiply by 24 hours day.
The key is consistency. Either multiply SIGI hour by hours, or multiply SIGI a by days.
Precisely. The time unit in the denominator of the rate must match the time unit of the mean life.
Okay, let's make that concrete. Say TR is for iodine 125 is 60 days.
Then TR at 1.44 60 days equals 86.4 days.
And let's say the initial dose rate, D, is 10 SIGI hour.
See the mismatch. SIGI hour in days, you need to fix it.
Option 1. Convert to hours. 86.4 days, 24 hours day, equal 73.6 hours. Now I can multiply D, 10 CDR, by 2073.6 CDR.
Right. Option 2, convert D 10 CDR, 24 hours day equals 240 C hours A by 10 C day by 26.4 days.
Both methods should give the same final answer for the total dose, right?
They absolutely should. It's just about making the units consistent before the multiplication.
Okay, that unit check is vital. So once D and 10 have matching time units, step 4 is...
just multiply them. Total dose equals D. The time units will cancel out, leaving you with just units of dose, like Saru or Gray.
Can we use an analogy for this one too?
Let's try the light bulb one. Think of the seed as a tiny light bulb. The initial dose rate, DU, is how bright that bulb is the instant you switch it on its peak brightness.
Okay.
The mean life is like the average amount of time that bulb effectively stays on or gives off useful light before its power source, the radioactive decay, fades completely.
So it's not how long until it's totally off, but the average on time.
Sort of, yeah. It represents the effective duration over which that initial brightness contributes. The total dose is then like the total amount of light energy emitted by that bulb over its entire lifetime.
So if the bulb starts brighter, higher D.
Or total light.
Or if it stays on longer on average, higher D.
Or total light then, too. Total dose, brightness, average duration, DU.
And a quick check.
If you imagine using an isotope with double the half-life, its mean life, 1.44 gyros, will also double. If the initial dose rate D were the same for this hypothetical isotope, then the total dose, D low, should also double. If your calculation doesn't show that, check your math and units.
Got it. And this calculation is what informs the prescription for permanent seeds.
It's a fundamental part of it. The doctor prescribes a target total dose, say a 145 gray for prostate. The physicist uses this principle combined with sophisticated computer planning based on imaging to figure out how many seeds of a specific activity, which determines D eras near the seed, are needed, and where to place them to achieve that prescribed total dose throughout the target volume.
So getting D euro right is critical for hitting the dose target.
Absolutely vital. You don't want to underdose the tumor or overdose the surrounding normal tissues.
Okay, we've covered the how. Let's talk a bit more about the why. Why is really mastering these specific calculations so important beyond just passing exams? How does it translate to patient care and safety day to day?
Oh, massively. Think about radioactive decay. Knowing how to calculate remaining activity is essential for managing your HDR source. When was it calibrated? How much activity is left today? That determines the treatment time for the very next patient. Get it wrong, you mistreat the patient.
And source exchange frequency too, right? Knowing when it's decayed too much to be efficient.
Exactly. For unsealed sources, like iodine-131 thyroid therapy, decay calculations tell you how much activity is left in the patient over time. That dictates when their radiation levels are low enough that they can safely go home or stop specific radiation precautions according to regulations. It's patient discharge criteria.
An effective half-life.
That's the bedrock of nuclear medicine dosimetry, as we discussed. Accurately estimating the dose to organs requires knowing how long the radiopharmaceutical actually stays there, considering both physical decay and biological clearance. It guides how much activity to administer in the first place.
And the permanent implant dose calculation.
Directly ensures the prescribed dose is what's likely to be delivered. Underdosing risks cancer coming back. Overdosing risks serious side effects like rectal or bladder problems after prostate seeds. The DOID calculation is the bridge between the prescription and the actual physical plan with the seeds. Accuracy here is paramount.
So yeah, these aren't just obscure physics details. They are woven into the fabric of safe and effective treatment planning and delivery.
Absolutely, every single day.
Okay, let's distill this down. What are the absolute must-remember clinical pearls for these topics, the things you really need to have locked in?
Okay, pearl number 1, know your basic decay formulas, AT, and the other form, ATA 0.5, and the link, 0.693 T euros. Those are non-negotiable.
Pearl number 2, effective half-life. Remember, the formula uses reciprocals, 1T effective, 1T physical, plus 1T biological. And the crucial takeaway, T effective is always the shortest of the three. And don't forget to take the reciprocal at the end of the calculation.
Pearl number 3, mean life, tau. It's related to half-life by that factor of 1.44. So 1.44 tier used for permanent implant dose.
Pearl number 4, total dose for permanent implants. It's simply initial dose rate times mean life, total dose equals D euro. But the absolute golden rule here is units. Match the time units in D euros before you multiply. Hours and hours or days and days.
And pearl number 5, it really helps to have a feel for the half-lives of commonly used isotopes. It gives you context. Iridium-192 for HDR, about 74 days. Iodine-125 seeds, about 60 days. Palladium-103 seeds, faster, about 17 days.
What about the longer-lived ones?
Cobalt-60, used historically in teletherapy and sometimes now in gamma knife for specialized HDR, is about 5.26 years. Cesium-137, used in older LDR implants, is around 30 years. Just knowing these rough numbers helps you sanity check calculations or understand timescales.
Excellent pearls. Okay, feeling ready to test ourselves. Let's do a quick board review blitz. Have your calculator handy or just follow along with the logic.
Let's do it.
Question 1. You have a 100 millicurie source of palladium-103. Its half-life is 17 days. If you leave it on the shelf for 34 days, approximately how much activity remains? Your options are A, 100 milliuri, B, 50 milliuri, C, 25 milliuri, or D, 12.5 milliuri.
Okay, let's break it down. Half-life T is 17 days. Elapsed time T is 34 days.
First step.
How many half-lives have passed? That's T divided by T. So 34 days, 17 days equals 2. Exactly 2 half-lives.
Okay, 2 half-lives. Now what?
Apply the halving principle. Start with 100 milliar. After 1 half-life, 17 days, it halves to 50 millisii.
And after the second half-life, total 34 days.
It halves again. Half of 50 millisii is 25 millisii.
So the answer should be 25 millii. Can we check with the formula?
Sure. AT A30.5 raised to the power TT here. A34 days over 100 millii obeyed cyber raised to the power 304.17.
Which is 100 millii at 0.5.
Right. And 0.5 squared is 0.25. So 100 millisii, 0.25 equals 25 millisii. Matches perfectly.
So the correct option is C.
Correct. 2 half-lives always leaves you with 1/4, 0.50.5 of the initial activity.
Great. Question 2. A new radiopharmaceutical is developed. It has a physical half-life of 12 hours. It also has a biological half-life, due to clearance, of 12 hours. What is its effective half-life? A, 6 hours, B, 12 hours, C, 18 hours, or D, 24 hours?
Okay, this is an effective half-life problem. T physical plus hours, T biological equals 12 hours. We need T effective. 1 T effective, 1 T physical plus 1 T biological. First, check units. Both are in hours. Good.
So plug them in.
1 T effective equal 112 hours plus 112 hours.
Add the fractions.
112 plus 112 equals 212 per hour, which simplifies to 16 per hour.
Okay, 1 T effective equals 16 per hour. Now what?
Right now, the crucial step. Don't forget the flip. We have 1 over T effective. We need T effective.
Take the reciprocal of both sides.
So T effective equals 61 hours. We're just 6 hours.
Let's use the mnemonic check. T effective, 6 hours, must be shorter than both T physical, 12 hours, and T biological, 12 hours.
It is. So 6 hours makes sense. The answer is A.
And if you forgot the flip, you'd have 16, which isn't an option, but it highlights the importance of that last step.
Absolutely. Common trap.
Okay, last blitz question. Question 3. You're planning a permanent iodine 125 seed implant. The initial dose rate right next to a seed is calculated to be 10 centigrade per hour, 10 CJ. The half-life of iodine 125 is about 60 days. What is the approximate total dose delivered by the seed over its entire lifetime? A, 86.4 gray, B, 144 gray, C, 207.4 gray, or D, 240 gray?
All right, this is total dose of euro. We're given D error for CR. We're given T errors 60 days.
A step. Find the mean life tau.
Right. 1.44 T. So 1.44 is 60 days. Let's calculate that. 1.4460 equals 86.4. So it's 86.4.
Okay, 46.4 days. Now, step 2, Check units before multiplying.
Crucial step. D is in CG per hour. Hour is in days. They don't match.
We need to convert. Which way is easier?
Let's convert D to CRQ per day. It's 10 CG per hour. There are 24 hours in a day. So DR is 10 CR, 24/3A equals 240 CR.
Okay, now we have DR 240 CR and TO's 86.4 days, units match days.
Perfect. Now we can multiply. Step 3. Total dose equals DO.
Total dose equals 240 CR to 86.4 days.
The days cancel out. 240, 86.4 equals 2736. The unit is centigrade.
So total dose equals 207.36 Sirajoy.
Okay.
But the options are in gray.
Right. We need to convert Sirg to G. Remember, 1 gray was 100 centigrade, so we divide by 100.
207.36 gray.
Now look at the options. 207.36 gray is closest to option C, 200.4 gray.
So C is the answer. And that unit conversion was absolutely essential.
Totally essential. If you'd multiplied 10 Sijiri by 86.4 days directly, you'd get 864, which isn't even close, and the units would be meaningless. Unit vigilance.
Okay. 3 key calculations navigated. You know, it reminds me of a joke. Why did the physicist break up with the biologist?
Uh-oh, why?
Because they had no chemistry, and their relationship had reached its effective half-life.
That's painfully relevant to our discussion.
It does feel like a lot to juggle sometimes, especially studying for boards.
It does. But you know, while that joke might feel relatable right now, the amazing thing is, with practice, these calculations, the formulas, the unit checks, they genuinely do become second nature. They really do. You start to just see the relationships and anticipate the steps. It gets embedded.
Absolutely. And maybe a final thought for everyone listening. We talk about biological clearance as something we measure to calculate dose.
Yeah.
But what if we could actively control it?
Interesting. You mean like designing drugs or methods to make the body clear a radiopharmaceutical faster from healthy tissues but keep it longer in the tumor?
Exactly. Or maybe the reverse for certain applications. Could we manipulate biological half-life, P biological, to improve therapy or imaging in the future?
That's a really exciting thought. Using our understanding of T biological not just passively for calculation, but actively for therapeutic modulation, it definitely builds on these fundamentals. And remember, even current advanced techniques like PET scanning, pronounced PET, fundamentally rely on tracking these radioactive decay events precisely in space and time.
It all comes back to these core principles. So today, we really broke down radioactive decay, that crucial concept of effective half-life, and how to calculate the total dose from permanent implants.
We hit the key formulas, the step-by-step approaches, and hammered home the importance of checking those units.
Keep practicing these. Work through problems. It's the best way to make it stick.
Absolutely. They're foundational tools you'll use throughout your career.
You can find resources like practice oral boards over at RadonSmartLearn.com. That's RadonOncologySmartLearn.com. And be sure to subscribe to Radon Smart Review for our next session. Thanks so much for tuning in.